Okay, I'm going to go through a couple more examples from 10C in case you need some more help with the K-value aspect, finding quartiles. So if we look at this question 1, it says, consider a population of crabs where the length of a shell, so they're measuring the lengths of the shells of crabs, is normally distributed with a mean of 70 millimeters and a standard deviation of 10 millimeters. Okay, so we're going to say that X is approximately normally distributed with a mean of 70, that's the first number listed, and then a standard deviation, we always put a squared on that, of 10. So what we're trying to determine is, it says a biologist wants to protect the population by allowing only the largest 5% of crabs to be harvested. He therefore asked the question, 95% of the crabs have lengths less than what? So we only want to take the largest crabs from this population. We want to leave the smaller ones to continue to grow. This would allow them to kind of keep the population under control. I don't know, whatever they're doing this for. So it's normally distributed. So to kind of get a visual of what's going on, we have a bell-shaped curve. Our central number is our mean, and so 70 millimeters for the crabs. And then standard deviation of 10, so it would go up by 10s and then down by 10s. At some point along here, it's probably up here pretty far. At some point, I don't really know where, 95% of our data is smaller than, and 5% is bigger than this shell length. Okay. I put the line over here because I know 95% is less. This is our 50% mark, right? 100% is going to be over here somewhere. So 95% is less. We want to find that shell length. To do this, this is our inverse norm button on our calculator. So I'm going to press the second vars. We want to go inverse normal. And it asks us for a couple of things. So we're going to, second, it's our distribution, which is a normal distribution, so that should help you know to find it there. And then we did inverse norm. And we're going to indicate some values. So the area is always the percentile. It's always the percent less than. So we want to use, although we want to say the question asked, allowing only the largest 5%, we have to indicate that we want the value where 95% is less. So we're going to use 0.95. Our mean was given as 70. Our standard deviation given as 10. So here's our screen. So 0.95. Our mean was 70. Our standard deviation of 10. When we press enter, it tells us 86.4. Okay. So that would mean that if you were maybe fishing for crabs, that you could only harvest crabs that are greater than 86.4 millimeters. So if they're this big or they're smaller, we can't harvest them. They would fall in the 95%. So at 86.4, 5% are bigger, 95% are smaller. Okay. All right, example 2. So they give it to us in this notation. Remember, the first number is your mean. I'm calling it mu here. Our standard deviation sigma is that 3.1 value. They want us to find k, for which the probability of our variable being less than k is 95. So because it's this less than sign, we're looking for at some point 95% is less than. This is similar to our last question. So there's some value right here is our mean, which is 23.6. We want there's at some point here, at some k value, 95% is less than. So second vars, inverse normal. We have our 95%, and then our mean is 23.6. Standard deviation is 3.1, and it should spit out a number for us of 28.7. Okay, so the value 28.7, if x is less than 28.7, 95% of our data is there. So you can think that's our k value. The probability of a random we choose something from whatever this is about, whatever this data is about. We choose a random data value. The probability that that data value is less than 28.7 should be 95%, and that's what we found there. Okay, example 3 says if Z is the standard normal distribution, find K such that the probability of Z, that Z is greater than K, is 0.73. So if the probability Z is greater than K is 0.73, the probability of Z is less than or equal to K has to be the rest, okay, the 0.27. All right, the standard normal distribution, you don't have to memorize this, but the standard normal distribution has a mean of 0 and a standard deviation of 1. Okay, so that probably should have just been included in the problem. You don't have to have that memorized, but here we go. Second, distribution, inverse norm, because we're trying to find our K value that gives us this area, or this probability. So we have to use the less than. So we want the original question says we want to find some value where our variable is greater than that value is 73%. So we want to do the less than, always the less than, the area smaller than. So I want to do 0.27. My mean is 0, my standard deviation is 1. And so at negative 0.613 is that value right here. Okay, where 27, this is our mean of 1, or 0, sorry. 27% of our data is smaller than that number, 73% is bigger. Okay, example 4, the students of class X sat a physics test. The average score was 46 and a standard deviation of 25. The teacher decided to award an A to the top 7% of students in the class. Assuming that the scores were normally distributed, find the lowest score that would achieve an A. All right, so this is normally distributed. Typically with tests, they would shoot for a normal distribution on tests, especially like large standardized tests like the ACT, the SAT, that type of thing. They do shoot for a normal distribution. So we have this data. 46 was the average. Standard deviation of 25. Okay, so every mark, right, 25 each one. The top 7% of the class is going to get A's. So that's going to be over here somewhere. 7% is large. There's some value where 7% of the kids got more, and that means that 93% got less than that mark. So we want to use the 93%, not the 7. So we're trying to find the test score, the cutoff line, where 7% got better than that score and 93 got less than that score. To do that, second distribution. Number 3, inverse normal. Our area is 0.93. Our standard deviation is 46, and they told us our mean is 46. Our standard deviation is 25. A mean of 46, if that's percent, that would be very low. Our standard deviation is 25, and so he would be awarding A's to anybody who got greater than an 82.9 on the test. Anybody lower than that would get lower than an A. So the cutoff would be 82.9 points scored on the test. That would give 7% of the kids would be bigger than that score. 7% would get an A. Everybody less than that would receive less than an A. All right, last example here. A university professor determines that no more than 80% of this year's history candidates should pass the final examination. So we only want 80% to pass, no more. So the examination results were approximately normal distributed with a mean of 62, standard deviation of 13. So 62 is our mean, our standard deviation of 13. Okay. Find the lowest score necessary to pass the exam. So there's some cutoff, I'm just making a guess, where 80% We want 80% of the students to pass. That means we want 20% to fail. Okay, a university professor determines that no more than 80% of this year's history candidates should pass the final exam. So at whatever number this is, whatever score number that is, 80% of kids got better than that and 20% got less than that. So we have a mean of 62, a standard deviation of 13, and we want to use the 20% value because we need to use the percent that's less than our whatever mark we're trying to find. So we will use for our area for this one the 20%. So inverse normal. Our area is the 0.20, 0.2. Our mean is 62, and our standard deviation for this exam was 13. Mean is 62, standard deviation of 13. So you would have to receive a 51.1 on this test, or greater, to pass the examination. All right, I hope this helps clear up maybe a little bit from 10C. As always, let me know if you need some help with this content.